So welcome. This is lecture number 1 of our course on basic electrical engineering. In this course, we'll be understanding we'll be analyzing both DC circuits as well as AC circuits. We'll be deriving the mathematical models of these circuits. Through those mathematical models, we'll try to understand how a certain circuit behaves, and we'll be looking at both their transient behavior as well as their steady state behavior. So we'll be doing both the DC circuit analysis as well as the AC circuit analysis. But to start with, our first unit of our course will be going through, actually reviewing some of the things that you've already studied previously at your 10+2 level, and we'll be looking at some of the basic concepts related to electrical circuits. We'll be looking at a number of electrical circuit parameters. So we'll take someone to 2 to 3 lectures to cover up our unit first of our course on basic electrical engineering. In this lecture, in this unit we'll be understanding the basic properties of any electrical system. We'll be looking at the fundamental components that are associated with any electrical system, and how a circuit will behave in ideally as well as a practical electrical circuit, how it will behave differently from that of an ideal electrical circuit. Right? We'll be also looking at different sources, voltage sources as well as current sources, how they can be interchanged, how a voltage source can be converted into a current source, how a current source can be converted back into a voltage source, and how actually a voltage source and current source, how they are different from one another, and how they will behave ideally as well as how they will behave in a practical circuit. So that will be covering up in unit 1 of our course. To begin with, we'll take a simple definition of an electrical circuit. So as far as an electrical circuit goes, it is simply, we can define it as an interconnection of a number of electrical elements. Now, what are these electrical elements? These electrical elements can be active elements, or they can be passive elements. So we'll be actually going through both active elements as well as passive elements. We'll be understanding the properties of both of these elements. So any electrical circuit will have a combination of different electrical elements. Now these electrical elements can be either an active element or a passive element. An active element is something that is able to generate voltage or current on its own, fine, or it's a source of energy, in other words. While as a passive element, it is not a source of electrical energy. It cannot generate electrical energy on its own. It can be a sink of electrical energy. That means it may be able to consume electrical energy, or it may be able to transfer electrical energy, but it is not able to generate electrical energy of its own. Not able to. Fine. So that means we can simply say a battery is an active source, while as a resistance is a passive source. There are, apart from battery, there will be a number of more active elements that you will encounter throughout your course, as well as pass-through elements. You have resistance, inductance, capacitance, etc. So again, you will be encountering a number of pass-through elements, and you'll be learning more and more about these things as you move on. So an interconnection between these elements makes up an electrical circuit. So most likely an electrical circuit will have at least one active source and one active element, and it will have at least one passive element. Fine. So we can have a simple electrical circuit like this. You have a simple battery here connected to a bulb. We can show a bulb, simply model it as a resistance. Fine. This is our load resistance. So this here represents the simplest electrical circuit. It's an interconnection of just two elements. One is a battery and one is a resistance. Nothing more than this. So an electrical circuit is an interconnection of electrical elements. Now if we talk about more about electrical circuits, we can even have some complex circuits like this. You may have a diode installed in a circuit, you may have an inductance, you may have a capacitance. I'm just this may not, how this circuit is behaving, I may not be able to tell that right now, but I'm just showing interconnection of different elements. You can have switches, so you have a circuit like this where you have a voltage source, you have a diode, you have a capacitance, you have an inductance, you have multiple resistances, you have switches operating in this system. Fine. You may have a current source also in the system. So a number of active elements are present in the system. Here you have the voltage and inductance, and you have some passive elements also present in the system. So this here represents a somewhat of a complex electrical circuit. So you have some simpler electrical circuits, you have more complex electrical circuits. So as we progress through our course, we'll be encountering more and more complex circuits. So we'll be starting with basic electrical circuits, a simple resistive circuit, a simple inductive circuit, a simple capacitive circuit, and move on through this course and encounter more and more complex circuits where we'll be having a combination of these different passive elements, a combination of different electrical active elements. So an interconnection of that will result in a more complex circuit. How to analyze these circuits, how to find out the current through any branch of the circuit, how to find the voltage in any branch of the circuit, how to find the power consumed by any element in the circuit, any passive element in the circuit, what is the power generated in the circuit by the active sources. So all of that we have to determine. We have to also look at their transient behavior as well as their steady state behavior. So how voltage actually builds up in a circuit. So that we'll be looking at briefly. Now associated with an electrical circuit are two important terms. One is current and another one is voltage. In order to understand current, we need to first of all understand what charge is. So charge is a fundamental unit. It's a base. it is an electrical property of a system. Uh, it is an electrical property of an atomic particle, and we know that uh, we have protons positively charged, we have electrons as negatively charged elements. So there, it's a fundamental property, one of the fundamental properties of a system of any element, and it is defined one. It is measured in terms of coulombs. Fundamental property of atoms measured in coulombs. See, so one coulomb is actually defined as the amount of charge that 6.24 into 10 raised power 18 electrons fine. One coulomb is actually the charge of 6.24 into 10 raised power 18 electrons. We have both positive charge as well as negative charge, and we know that current is actually the flow of negatively charged electrons in a circuit. Or in other words, we can simply say flow of electrons is what constitutes a current. Electrons carry negative charge. It's the basic property of any atom, where it's measured in terms of coulombs, and one coulomb is actually the amount of charge carried by 6.24 into 10 raised power 18 electrons. We also know that one electron actually has 1.6 into 10 raised power minus 19 coulombs. And the movement of electrons is what constitutes a current. Current can also be now defined as time rate of change of charge. So time rate of change of charge is actually what is known as current, or we can say I is equal to dq by dt, and its units are ampere or simply A. So any atom has a basic property, a fundamental property, that is charge, which is measured in terms of coulombs. Now protons are positively charged and electrons are negatively charged. Now the movement of actually electrons is what constitutes a current. So when electrons move, I'm not saying what causes that movement yet. When electrons move, that is what current is. Now this rate of movement of this current, or you can say now charge, is what is current. Fine. So actually I is you can say it's equivalent to velocity in one way, where a certain distance is moved by electrons. Time rate of change of these electrons is what constitutes a current. Fine. So I is equal to dq by dt. So we have defined movement of electrons as current. Now what causes this movement? Why do electrons move? Electrons will only move when you apply some force to them, or you have to do some work to be able to move an electron across some distance. So that is known as electromotive force. So you are applying a certain force that is known as electromotive force or EMF to a charge. Say for example, this charge was located at any point A. Now you are moving it to another point B. So the amount of work that is actually done to move this charge across this from point A to point B is known as voltage. Fine. So voltage is, simply speaking, dW by dQ, where dW is work done. So we can actually say this is actually the work done to move a unit charge represented by Q here from A to B. In this particular example, we are saying that if a unit charge having a charge equivalent to Q is moved from A to B, the work that will be done to move this charge from A to B is what is known as voltage. Or you can also say there is some potential at this particular point. There is some potential of this charge at this particular point. So the potential difference between these 2 points is what is also voltage. So in any electrical circuit, you have a voltage and you have a current. Now we'll try to understand this by using an example of a mechanical example to see the behavior of an electrical circuit. Right? Say for example, this is my voltage source, and say for example I have a water pump. So here this water pump can be treated as analogous to a voltage source. So water pump has an inlet pipe from which water is actually coming, and it has an outlet pipe from which water is actually moving out. Similarly, this is a voltage source. It has wires on both ends, you can assume. What this voltage source is, say for example, it's a simple battery. It has two leads. One is positive terminal lead and another one is negative terminal lead. Now this battery has a potential and it wants to do some work similar to a pump. That pump wants to push water through the pipe. Similarly, this battery wants to push electrons across the circuit. It wants to push electrons across the circuit. It wants to push charge across this circuit. Now if we connect a resistance here, we are connecting a resistance across this electrical circuit, so as this becomes a closed circuit. Now once this circuit becomes closed, now the electrons have a path for current to flow. Earlier, when this was only a battery, this battery had some energy and it wanted to push electrons, but there was no path available to it so that through which it could push the electrons. Similar to that of this water pump here, there was pump, but it had the potential to do some work, but but it could not pump water through any path because there was nothing coming into this pump, nothing and similarly nothing would go out of the pump. So there was no flow of water there, there was no flow of electrons here. But once the circuit is complete, say for example you have a tank here that contains water. Now since this tank contains water, you can, now the pump is able to get water from some path and it will be able to push that water back. Now we are actually pumping the water back into the same tank. This is not something that you do practically, but we are just trying to draw a mechanical analogous circuit to an equivalent volt VR resistive circuit driven by a simple battery source. Okay? We are just trying to make an mechanical analogous circuit of an electrical circuit. Fine. So as we can understand the similar behaviors between the two mechanical and the electrical circuit. So you have a battery, a voltage source, you have a pump, a mechanical source. Voltage source wants to pump electrons, but unless the path is complete, it cannot pump electrons. So no current will flow. So unless the electrons flow, current will not be in the circuit. So as long as it was open, as long as this voltage source was open, current was not flowing because electrons did not have a path to flow. But once this circuit is closed, we have a closed loop. Now we have a path for electrons to flow. Now the electrons can flow and that will constitute the current. Now electrons actually flow in the reverse direction. Electrons will actually flow in this manner, and we have said that flow of electrons is what is current, but the convention has been to show current in the opposite direction to the flow of electrons. This is just a convention that we have adopted, wherein we show the flow of current in the manner opposite to that of the flow of electrons. Electrons will actually be flowing from the negative terminal of the battery into the positive terminals. They will not be flowing from positive terminal to negative terminal, but we show the current from positive to negative terminal. This has been a convention that we have adopted, and it has been universally accepted. In a similar manner, just like a pump is pumping water into the tank and it is getting water back from the tank and pumping this, there's a continuous flow of water now here. Similarly, as long as this voltage source is connected to this resistance, it will be driving electrons through this resistive circuit. Now why did I show this tank to be constructed here? If you have a very narrow tank, narrow sized tank like this, or a nozzle, whatever it is, the pump will have to do more amount of work to actually pump water through this gap. If this path would not have been so constricted, if it would have been a very broader or a more wider tank, fine. So lesser amount of work would have to be done to move water through this pipe. Similarly is the case here. More the value of resistance, the voltage source will have to do more work, fine. Or you can say current through this path will be restricted, like water will be restricted if the tank is constricted. Similarly, if more is the resistance, more you can say lesser tank, lesser, if the tank width is less, you can compare it to more resistance. That means actually more resistance is being offered to the flow of water. Similarly, if you have a bulb that has more resistance, it is offering, it will actually allow very little amount of current to flow through it. So current will decrease. So if a value of R is more, I will be less. If value of R is less, I will be more. It's similar to in the mechanical terms, we can say if the width of tank is small, that's actually meaning to say that it will actually offer more resistance to the flow of water. So flow of water will be less. This actually equivalent to more resistance. And if width of tank is large, that's actually saying resistance offered by the tank is now smaller, flow of water will be more. Fine. So we have a mechanical analogous circuit to an simple resistive circuit and simple electrical resistive circuit, where pump is equivalent to voltage, where flow of water is equivalent to current. Fine. So current is actually also flow of electrons. Like flow of water, you have flow of electrons. Now at which rate water is flowing through this mechanical circuit, a pump and pipe circuit, similarly at what rate the electrons are flowing through this circuit, they will determine the value of current. Fine. So current is actually analogous to velocity in case of a mechanical circuit. Time rate of change of water in this pipe is equivalent to time rate of change of charge in an electrical circuit. That's actually current. So as long as this path was open, voltage source was there, it was ready to push, it had energy, but it could not push electrons because there was no path for it to push electrons through. But once the circuit was complete, now it has a path. It will the electrons will now begin to flow in this electrical circuit, and current will be current is actually the flow of that electrons. Fine. Now what in what we will be seeing is that we'll be making use of analogous circuits in time to time in a number of situations. Most often when you will actually study control systems, there you'll see what will be the you'll actually take a note of analogous equivalents of electrical circuits in terms of mechanical equivalents of electrical quantities. You'll see there in control systems 1, that will be actually taught in your 4th semester of electrical engineering course. So why that is important? Electrical circuits are actually very fast circuits. Their transient response is very small. Their steady state response is better. So electrical circuits are very fast. If you switch on, instantaneously the bulb will glow. Mechanical circuits or other forms of circuits, they are a bit slower. You will not see water suddenly rising up to the tank. It will take some time, 3, 4, 5 seconds for water to be pumped from one place to another place. It does not flow at the speed of light like electrons are actually flowing at the speed of light. Electrical circuits are very fast. So what we tend to do is mechanical circuits or structural engineers, mechanical engineers, civil engineers, they try to represent their systems, their structures, mechanical equivalents, pneumatic systems in terms of electrical quantities, so that they can understand the behavior of those systems in terms of electrical quantities, because analyzing electrical quantities is much easier and much quicker as compared to analyzing pneumatic systems, mechanical systems, or any structural systems. So you will encounter these problems where you have to derive a mechanical analogous equivalent circuit of an you actually have to derive an electrical analogous equivalent of mechanical systems. So I was actually defining voltage and current. Voltage, so you have to start with charge. Charge is the basic fundamental property of an atom. you have both positive charge and you have negative charged particles. Negatively charged particles, that are electrons. Now the flow of these electrons in a closed circuit is what is known as current. The direction which actually current flows is reverse to that of actual movement of electrons. Right? We conventionally the direction of electrons and direction of current has been taken differently. Although it is the flow of electrons what actually causes current in the system. Now, this flow of electrons assist any charge will not move from point A to point B unless you apply some force, unless you do some work, unless you are spending some energy on that system. Now this work or energy what we are talking about, this force that you need to push charge from one point to another point is what is known as voltage. So you have voltage and you have current. These are two basic definitions that any electrical circuit requires. So you'll have to note three more things: power, work, and energy. Now what is power? Power is simply you are now moving this charge from one place to another. So for that it requires work. You need to do some work, you need to spend some energy, so it will require some amount of power to be consumed for this charge to be moved from one place to energy. So power is simply the time rate of expending this energy. So we can say power is equal to dW by dt. We know that dW, I can also represent it as dW by dq into dq by dt. Why did I do this? Because dW by dq we have already said that this is voltage, and dq by dt we have already said this is current. So power is actually measured in terms of voltage and current through their multiplication, and the units of it are watts, represented by W. Now this V into I is actually instantaneous power. So this actually represents what is the power at any particular instant. It does not represent the actual nature of power expenditure in the system. That will be looking as we towards actually when we will be talking about AC systems. There it will be discussed more in detail. So any system, any element in an electrical circuit, be it is an active element or a passive element. An active element will be supplying power. It can also be actually consuming powers at sometimes. So as a passive element will be similarly a sink of power, and it may be also supplying power in some instance. Fine. So again, these things will be learning in more in detail. In general, an active element supplies power. Passive element absorbs power, consumes power. An active element will supply power. A passive element will consume power. In general, this is not necessary. A passive element may also supply power at some times, while as active element may absorb power at some times. Fine. So if a system supplying power is known as positive power. If power is positive, it means power is being supplied by that element. If power is negative, it means that particular element is consuming it. So this is what power means. As far as then we have work. Now we do not represent work exactly. Then we have energy. Now why energy is important? Because you are actually charged in terms of energy. How many units you are consuming you are charged for that. That unit is actually a measure of energy. How much energy you have consumed is what is known as uh, is what you are actually charged for. So energy, we actually know it's actually represented by it is measured, it is how much work you are doing, its capacity to do work, and it's measured in terms of joules. But when we are talking about electrical systems, we represent energy in terms of watt hours. Fine, how much amount of power is being consumed in in how much amount of time. Fine, so if you are consuming 1 kilowatts of if you are running a geyser, that's actually rated 1 kilowatts. If you are consuming, if this geyser is on for 1 hour, so that means you are actually consuming 1 kilowatt hour of energy. That means actually 1000 watt hours of energy. Now 1 kilowatt hours of energy is actually what is measured by our electric meters, power meters. So 1 unit is equal to 1 kilowatt hour. So we are charged based upon how much kilowatt hours of energy we are consuming. So these are some basic definitions: voltage, current, power, and energy. We'll learn more about these things as we progress through. In AC circuits, power is much more important. You will come across a number of definitions of power, and you will learn about different things about power. So we'll be doing some numericals on this on these things in the next session, as well as we'll be taking up different types of energy sources that we'll encounter in our course in the next lecture. So that's all for this particular lecture.